Okay, let's look at another example based off of data that we have. So a relative frequency distribution given in table 1, boom, represents the heights of a pediatrician's 3-year-old female patients. So this is heights here in inches. So, and the relative frequency, like how often that happens, right? So we learned that, again, previous information into the current lesson. The raw data indicate that the mean height is 38.72 inches with a standard deviation of 3.17 inches. So we're going to draw a relative frequency histogram. Boom, I have that for you already right here. And comment on the shape. So this data is what's used to make that histogram. So I'm going to make this bigger so we can talk about it. Look at that histogram. What do you notice about it? What do you think? What do you about the shape? Remember, right skewed, left skewed, bell shaped, symmetric, right? Those words mean the same. What do you think this one is? Yeah, I agree. Look at this. Looks pretty bell-shaped to me, doesn't it to you? So it would be considered a symmetric graph, right? Which is bell-shaped means, I'm going to put bell-shaped right here, just so that we can have those words, which means we can use the empirical rule. That's nice. Anytime I have that nice bell-shaped curve, then we can look at that and be able to use that empirical rule. Nice. Okay, so now look at this. Now, based on my data, I mean, we put a little highlighter one in there, but check this out. This is the same histogram down here. However, we're going to draw that blue, they did it for us, normal curve on there, with the mean and the standard deviation already given. We want to compare the area of the rectangle for heights between 40 and 40.9, which is right before 41. It's this green one here, to the area under the normal curve before the heights. So they're saying, what's the height of this piece under the normal curve versus the height of this rectangle? I went too far, didn't I? The height of this rectangle. That's what it's saying, making that comparison. So look at what's happening here. There's a tiny little piece over here. There's a little bit to the outside. What do you think? Do you think that that's fairly close to the same area? Yes, I do too. So if I'm looking at this, I'm going to squeeze this in so I can write on it a little bit. This is very close. So because that is, since the curve hits the rectangle basically in the middle. Rectangle, tangle in the middle. Let me try this again. Rectangle is what that word says, contrary to what it looks like. Rectangle. I'm glad you guys put up with my writing. Good thing I say it, right? So you actually know what it means. So this is very close. And notice how it's basically hitting that rectangle right in the middle. So kind of splitting it in half between what's under the curve and what's outside of the curve. And then those kind of even themselves out. All right, so when I have a rectangle like this, because they are so close, we can use the area under the curve. Area under the curve to approximate the height in the 40 to 40.9 inches option, because that's what it asked us. So because this is so close, I don't have to worry about that. We know that this is an empirical rule, so the area under the curve makes that empirical rule. And that's nice because these rectangles are so close. If we split it up in rectangles, we don't have to do length times width every single time. because this is nice and close, we can just look at this area under the curve, and we can do that by using the empirical rule. Pretty cool, right? I think so. So let's look at this area a little bit more. So the area under a normal curve, we're going to suppose the random variable x is normally distributed with a mean and standard deviation. The area under the curve for any interval represents the proportion of the population with the characteristic described, the probability that a randomly selected individual from the population had the characteristics described. All right? So here's what we're learning. The fact that I can talk about a proportion or I can talk about a probability, both of those pieces of information are going to represent the area. Both of these pieces of information are going to represent the area under the curve. So anytime you are asked to draw the area under the curve, that is what you're talking about. You can get the proportion from that. You can get the probability that that's going to happen. All right? Okay, so the serum total cholesterol for males 20 to 29 is approximately normally distributed, so I'm told that right off, with a mean of 180 and a standard deviation of 36.2, based on the data obtained from the National Health and Nutrition. We want to draw a normal curve with the parameters labeled. So we know the mean is in the middle, and my mean for this is going to be 180. Then one standard deviation away, that's where those inflection points happen. That means I'm going to add one standard deviation, right? My mean plus one standard deviation would be 180 plus that 36.2. What is that? 216.2. And that goes there. And then my mean minus a standard deviation, 180, I missed my zero there, 36.2, what's that going to give me? 143.8. Is that what you have? Make sure I'm doing this right. Okay. And there it is. There's a normal curve. It's got a mean, and it's got plus one standard deviation, minus one standard deviation. Cool. Yeah. I mean, we're not getting too fancy here. It's just exactly what you think it would be. That's what's happening. All right. So an individual with total cholesterol greater than 200, all right, is considered to have high cholesterol. Shade the region under the normal curve to the right of x equals 200. Basically, this is just making sure, do you understand what the normal curve and what is happening here? So if this is 180, which where's 200? It's not all the way to a one standard deviation, but it doesn't have to be. That's why we have these kinds of problems. So just under one standard deviation, this is at 200, and then I'm going to shade underneath there to the right of 200. So higher than 200, this area, this probability, this proportion that is shaded right there, that is where you can determine if you have high cholesterol. Okay, this is really just show and tell right now. We're just laying the groundwork so that we can do something with it. All right, so suppose this area that we're looking at right here under the curve to the right is 0.2903. So this area is what's shaded, 0.2903. You'll learn how to find this area in 7-2, so sit tight. It's really awesome. We're just laying the groundwork. Provide two interpretations of this result. So I'm going to squeeze this back down here. What did we say? You're going to get two things out of this, right? You're going to get the proportion and you're going to get the probability. So let's talk about what this actually means here. Let me get it up high enough so where we can write on it. Here's our first one. We're going to talk about the proportion. So what does this actually mean? What is this telling us? Well, it tells us that the proportion of 20 to 29 29-year-old males that have cholesterol, have high cholesterol, is 0.2903. That's the proportion. The proportion of males that have high cholesterol is the same as that area that's under the curve, and that is denoted by this 0.2903. The second thing we're going to talk about is the probability. The probability that a randomly selected 20 to 29-year-old male has high cholesterol is same thing. The probability of that a randomly selected 20 to 29-year-old male has high cholesterol is 0.2903. So it's really just, we're saying the same thing, it's just the words are a little different. So the proportion of 20 to 29-year-old males that have high cholesterol is this. That's the part, that's the proportion, that's the piece of them that has it. All right, so that's another way to say the proportion. The piece is this. So the area under the curve is the same as that chunk, right? That piece of them. That's the proportion. The probability that a randomly selected male has high cholesterol is this number. Do you see the difference? It's the same value that you're talking about, but you portray it just a little bit different. So the probability that you randomly select any one of the males, I just randomly select one, the probability is going to be 0.2903. The piece of the pie of all of the males is that proportion of 2903. It's kind of cool whenever we use all this stuff and we're bringing it all in together. All right, so hang on to this because we're getting ready to use it in full force here in this next section, and we're going to bring all this together. It's getting exciting. I know, I'm with you.